Google announced a major embrace of Kotlin multi-platform, and tons of libraries that you use today in Android apps are gaining support for especially iOS and other platforms. And I even just learned about another one at the last talk in this room, so it's like popping up everywhere. So focusing back on the offline first use case, really, we're so chained to the cloud. And we're used to communicating with the cloud and getting all of our data from the cloud. But very often, in a lot of use cases, you're on the train going somewhere, you're on a plane, you're on a boat, you're wherever. There's a lot of places where there's not network coverage. So offline first is a good start. Like, I need my app to function when I don't have internet. But what if you could have some bit of networking even in those offline use cases? You want a consistent experience, both when you have network and without, and you want a consistent experience across multiple platforms. So if you bring all this down to the data layer and have your data be the same, then that's one of the main points where you can simplify things, like if you're calling a service and iOS and Android are talking to two different services and the data model is slightly different, you get pain points there. So really, it has to be boiled down to the data layer to think about what's my consistency. And you could build this today with your own efforts using something like SQLite, Data Store, Room, or even Store 5, which, by the way, all of those have multi-platform support now. The Google ones, it's all like alpha level status support for iOS, but it's popping up everywhere, which is surprising. So we need to start thinking about, how are we going to do this? Are we going to actually, start code sharing with iOS? Because it's very within reach. So how are we going to do this? We want to focus on the data layer. We want to support multiple platforms, and we want to send data from peer to peer. When we're talking with the service, we're always going back to that cloud, and we're getting data from the cloud. So what's happening in the cloud is that's where the source of truth is. If I add a record or change a record, add a new message to text someone, that the server does all the bookkeeping to make sure there's a source of truth, and here's the current state of the chat message or your order or something like that. If we're going to do peer-to-peer, where's the source of truth? Is it you? Is it you? Is it you? I mean, it gets very confusing. So you really have to think about, how are we going to resolve conflicts or deal with inconsistencies? And that's kind of the whole point of looking at this. So first off, before we start sending data, we need to get connected. There's several different methods we can use to talk between different devices. And local area network is, it's been around forever. You've got a Wi-Fi network that sits on top of a local network. And we often don't think about this because this looks the same to our app as talking to the cloud. It's just a network connection away. But you can find other peers over a single connection under certain conditions. The biggest thing about it is on a network like the university network here, I couldn't get broadcast working. And that's usually locked down because of security reasons, because you'd use that same sort of broadcast to feel out the network and find someone to potentially go hijack their phone. So they get locked down for that reason. But if you have a real business use case, you can configure the network to allow broadcasts and allow peers to find each other. And what's awesome about this is you've got high bandwidth connections, you've got a single connection to the network, and you can have multiple peers on the other side of it. And the range is actually pretty good. You can get sometimes up to 200 meters from the last access point. So don't discount this. This could work, especially in a case like a store or some physical location where you can configure all the devices and that sort of thing. So another option that's great for on the go is peer-to-peer Wi-Fi, and there's a few different flavors of this that I'm going to talk about. The champion here is Wi-Fi Aware, which has been around since Android 8, where two Android devices can establish a connection between each other, and this can go up to about 80 meters, and it's pretty high bandwidth, 128 megabytes per second. Apple has their own flavor called Apple Wireless Direct Link. That's what's used by AirDrop. And so it actually works very similarly to Wi-Fi Aware. The main thing is it's not compatible. This is not a cross-platform technology. There's some support for Wi-Fi aware, I think, in Windows and Linux, but there isn't a lot of hardware support. But on Android, it's all over the place. Now, on Android, there's actually one other type of peer-to-peer Wi-Fi called Wi-Fi Direct that actually came out in Android 4, but it does not work as well as Wi-Fi aware. I think Wi-Fi Direct is what's still used for a nearby share, but that's like sending an individual file. But in the field, we've actually seen Wi-Fi aware is much better, and it's been around for quite a while. So, definitely something that can be supported by most devices. But the downside of this is every single pair of devices, you're setting up a new Wi-Fi connection. So that gets really resource intensive. If you've got 4 connections to 4 other devices, that's like 4 Wi-Fi connections. And this is in addition to if the device has a Wi-Fi connection. So there are hardware limits I'm not familiar with, but this doesn't scale to huge levels. But it's great for quickly transferring files and that sort of thing. Plus, it stands up very quickly. And the distance champion of these technologies is Bluetooth Low Energy. So there's actually a few flavors of Bluetooth. There's Bluetooth Classic, which is what you typically use when you're pairing your headphones. You have to punch in that number and that sort of thing. That's great for streaming audio. But Bluetooth Low Energy obviously uses less energy, but has great range. There's no pairing dialogues. The big downside to Bluetooth Low Energy is 20 kilobytes per second. That's very small. That's great for chats, but if you're trying to send images or video, it's just going to tip over on itself. There are hardware limits on Bluetooth Low Energy as well, so you can't set up 1 million, and it is similar to peer-to-peer Wi-Fi where each connection is consuming resources. So it can get battery intensive if you're doing a lot of it. But this is fully cross-platform. You can talk iOS to Android to Windows to Mac, Linux, you name it. This will work. But it's very complicated to set up. Is it actually? Yes. So on our blog, we actually have a complete guide for how to set up core Bluetooth on iOS. And it is very complicated. You have to set up one side that is, one side is the peripheral that's connecting to the central, and there's this handshake that goes back and forth. Who are you? I am this. I have these capabilities. Okay, you have those. I don't offer that one. Do you want to do this one? And it's this really chatty thing just to get the connection going. And I've talked to so many Bluetooth developers that say there's bugs in the spec and that sort of thing you have to work around. So it gets very complicated very fast. And that's just iOS. Android has its own APIs, which at the Bluetooth level might have some of those challenges, but I think the APIs are a little bit bigger, better on Android. But still, it's very complex to deal with these platform level things just to get that, yay, I have that blue connection that actually is cross-platform. The implementations are totally not cross-platform. So you're thinking, well, do I pick this one? Do I pick that one? What are we actually going to use? Well, putting that aside, because the transports may make more sense in one case versus another, whether you're going to have distance or cross-platform, or maybe they're all on Android, so I don't need to worry about Bluetooth. But even once you get established by one or more connections, actually sending the data from one device to another, you run into that problem that I mentioned. Where's the source of truth? You changed the message. Well, I auto-corrected that, and or changed this value over here. And who wins in that situation? We're talking, we could send the whole document. Here's my view of the world. Here's your view of the world. Diff it and go. Oh, okay. You said this. I said that. But we're dealing with limited bandwidth in some cases here. So if you get too chatty, you're defeating the whole purpose of setting up these connections. The connections come and go, so you always have to retry. There's tons of that back and forth. So this is where peer-to-peer projects go to die. You get it established, everything looks great, and then you deal with this for days because as your data model changes, as your protocol changes, you're just constantly going back and forth. And so there are a few approaches that you can get better at this, where if you have metadata related to the change, so like timestamps and a little bit of bookkeeping to help resolve the conflict. That can help, but it gets messy really fast. It helps if you can keep track of what data you sent to who, but all of a sudden you've got this whole separate database for every peer you've seen. And can I continue getting the same data from a different peer? Like, do they have the data? How do I ask for that? Like, these are complicated protocol questions. We're not going to get into all of that. I just want to call it out that, like, this is not a space you step into lightly. And there is a quick way to deal with all of this. We have an SDK called Ditto that establishes peer-to-peer connections using basically all the transports that I just mentioned. Plus, it can do cloud or a specific WebSocket connection if you want. And it will multiplex data across those connections, automatically fail over, all behind the scenes for you. And you're storing data into a database that will automatically replicate for you. And when the devices get too far away or you lose connection, data is still being stored, and then when they come back in range, it will replicate what's changed there. So how do we deal with all of this? Well, we did the hard work on the transports. We basically have all these transports to where they know how to connect. They send the data or they establish a connection, and we might decide to actually use Wi-Fi aware because that's more high performant than the Bluetooth that's available. So we'll seamlessly switch between any unavailable transports or pick the best one for the scenario. And so we'll see the rainbow connection in the demo where they're kind of coming, the connections are coming and going. But the idea is that at a high level, it's basically a virtual WebSocket connection to one or more peers. And our cloud, we actually call that the big peer because we do the replication exactly the same. It's diff-based sync we can totally continue, pick up the rest of the document updates that you might have missed because you were away from a different peer. And that's the magic of CRDTs. CRDT stands for conflict-free replicated data types. It's an efficient way to encode the data around a diff. Essentially, I changed this property, and here's my timestamp. And that can be replicated around and resolved later. So it's an eventual consistency system where you can apply those in any order and anybody can apply those. And as long as the same set of changes are applied to two peers, it will have exactly the same data. It's all theoretical and stuff. And actually, there's been papers written about it for like 30 years. And I believe we're one of the largest implementations of this, actually being used in production for stores and that sort of thing. It works really well, which is awesome. So low amounts of overhead in that metadata that's going out. So you can actually build really big meshes where all these devices are talking to each other, and maybe only a few of those have a connection to the cloud. Well, as you can see here in this diagram, we sort of have one mesh on one side and another mesh on the other side, and there's the big peer in the middle. So that might be two different stores where we might not be syncing the orders from one store over to another, but you could have, say, configuration data that's distributed across the entire mesh. And with our cloud product, which we're not going to focus on, we have all kinds of integration options for classic, legacy systems like Kafka and webhooks and so forth. But yeah, the beautiful thing is the cloud can go down, your Wi-Fi can go down, your store can still operate, you can still take orders, and your business can still function, or you can still continue chatting with someone, and then when everything reconnects, all the data just flows where it needs to go. Okay, so I want to shift gears now and see, now we have all this magic, but today, Ditto doesn't support Kotlin multi-platform. We do support iOS, we support Android, we support a whole bunch of other platforms. So I looked at pulling in our libraries to put them into a Kotlin multi-platform app to see how well does it work. And I basically got both iOS and Android in an app and syncing, and I could see some logs and tell that it was working in like 2 days. It was actually surprisingly easy. The pain came after that when I was trying to work with the API, especially on the iOS side, and we'll get into those details. But specifically what I was doing is our live.ditto package up on Maven Central is our Android SDK, and we have two SDKs for iOS. We have Ditto Swift and Ditto Objective-C. Now, I went with Objective-C because of reasons. So this is straight from their docs. You basically cannot use pure Swift in Kotlin multi-platform. So Swift can be compatible with Objective-C or not. And if it's compatible with Objective-C, it'll work with Kotlin multi-platform. But you're not going to find a lot of open source stuff that's still compatible with Objective-C. Swift has been out for a decade now, and iOS developers would love to get rid of Objective-C because Objective-C holds back Swift. There's some of the coolest features of Swift that you can't use if you're compatible with Objective-C. So the bridging between Objective-C and Swift is way more complicated than Kotlin and Java. And Swift is not supported, like pure Swift is not supported. But if it's compatible with Objective-C or it's Objective-C itself or C, you can use it in Kotlin multi-platform. And specifically, this is kind of what it looks like. So if you have a Swift class that extends NSObject or any class, like the root object is NSObject, so basically if it extends anything with NS or UI, then it is an Objective-C compatible Swift class. Now, you also have to have the methods be compatible, and it depends on if you use types that are not compatible with Objective-C, then you can't even annotate them with at Objective-C. But at Objective-C is a way to say, I want this to be compatible with Objective-C, and so you get compile errors if you try and use like an enum without a backing field or enums with associated values, things that Objective-C just can't see. So pure Swift, you're not going to see any of that stuff. Or you might have a class that has some things that are visible to Objective-C and other things that aren't. So yeah, that gets into the weeds. But like, you really have to look at what am I consuming and how much of that is compatible with Objective-C to do things in the way that I did here. I imagine Swift support will come soon, but it's just not easy. It's done totally differently than all other native things because Swift actually introduced this Swift interface file, which kind of serves as the header, but it's like nobody else does that. Only Apple did that. And they did that for module stability because the binary, they didn't have a way to guarantee the layout. So it gets complicated, but just there be dragons. Okay, so as I mentioned, there's 4 compiler backends to Kotlin multi-platform or the new K2 compiler. So the JVM and the native backend are the 2 that we're talking about. The other 2 are web-related, either generating JavaScript or generating WebAssembly. So the native backend is what is actually going to emit a native binary from the Kotlin code that you write in the common main section of a Kotlin multi-platform project. And speaking of a Kotlin multi-platform project, so if you go to there's a Kotlin multi-platform wizard online where you can just pick a couple options. I want this, I want that, and have it generate a project. The standard, so it has 2 options. One for shared UI, which is composed multi-platform, or one that's without the shared UI. It generates Swift UI for the iOS side. So if you do the without composed multi-platform, this is what you get. You get a top-level Android app, a top-level iOS app, and a shared folder. So shared is where the cross-platform code is going to go, and we're going to look deeper into that. But iOS app is just an Xcode project. That Xcode project will consume the output of iOS main because that generates a framework for the iOS side. And the Android app has some Android-specific stuff, and then Android main is the Android side of the Kotlin multi-platform that gets included in that. Now, if you check the other box and do a composed multi-platform, you don't get a separate Android app project. Android app is basically smashed into Android main in that style because it doesn't need a whole separate target for that. But if you're going to migrate from one to the other, there's a lot of Gradle dancing to get to the structure. So there is an iOS app like project just like the other one, and they actually call it common main in this style versus shared in or shared in common main versus just the app and common main in a composed multi-platform layout. So the demo app that I have is composed multi-platform because I didn't want to write the UI twice, and it's not that complicated, so I wanted to save some time on that. I spent a lot of time on the bridging stuff, so to pull in libraries that already exist, In Kotlin multi-platform, there's a source set section and then different configurations for these common main, Android main, and iOS main. And if you support other targets like desktop, you'd have other types of main in here. So this is where dependencies go. Common main would be anything that is pure Kotlin or Kotlin multi-platform. Now, some libraries I've noticed, like Ktor, actually has like an iOS client that's a different artifact than the Android client. And so anything that's platform specific goes in those Android main or iOS main. So you can see libs.ditto is the Android library that I added here. But there's a totally different way to include a native iOS, like one that doesn't have a library around it, which was the bulk of the work here. Okay, so this is just to zoom in and not use version catalogs. This is just standard Maven coordinates for adding the ditto dependency. Again, this goes in Android main, and this is going to be seen from the Android side of the multi-platform code. And so any other Android-specific dependencies that are used in that cross-platform piece go in there. Now, if you happen to drop a Android dependency in common main, and you're supporting iOS, but that dependency doesn't really support Kotlin multi-platform, you get these kind of weird errors where it's like, couldn't resolve all files for configuration. I actually dropped the Android X lifecycle model. I think 2.8 actually added multi-platform support, but this is 2.7, which doesn't have the iOS side, and it isn't until it tries to build that it realizes that's a problem. But you get these weird errors, like it's trying to build iOS for the ARM64 chip, and it's going to do C interrupt to look at it, and there's nothing to look at. So that's Gradle for you. Okay, so how do I add the iOS dependency? Now, this syntax was a little weird, and I suspect they may be changing this, but since Kotlin 2 came out, there's a little bit, some things are broken with this. So if you're going to consume an iOS dependency, you can consume it from CocoaPods. And actually, this was really easy because it took very little syntax, and boom, it was generating Kotlin for this. But if you notice, there's a whole CocoaPods block, and then down at the bottom, it says pod ditto Objective-C. Now, that pod is the dependency that I want to pull into the build. Everything above that is the configuration for emitting the framework for iOS. So it's a little weird that there's a dependency into the Kotlin build and sort of how I export in one thing. That's why I suspect this may be changing, because it's the dependency part that is broken here. But one thing I want to call out, the first thing you'll hit when switching to Kotlin 2 is it'll complain about this framework base name. And they made this required so that CocoaPods framework base name has to be set to something. They'll probably fix that in a bug fix pretty soon, but like that took me a long time to figure out. Anyway, so, oh, by the way, what is CocoaPods? CocoaPods is Ruby-based. You probably heard the term thrown around. And it's a package manager for iOS and macOS, all Apple platforms, but it's also an Xcode project generator. So while this is just building a framework and then making it available to Xcode, we're not really going through the whole CocoaPods mechanism. We're just using the Xcode generation. And actually, this is not a weird thing to do at all, because React Native and Flutter do the same thing behind the scenes. So CocoaPods is great for that. It's just a pain to deal with the Ruby dependencies. So pro tip, never use system Ruby on macOS. Always install Ruby, either RVM or brew install CocoaPods, because they put two architectures in the Ruby, and it's just a pain when you get to native dependencies. So you also won't have to do sudo on every single gem install. Okay, this is the issue I was talking about. So upgrade to Kotlin 2, and you get this weird error when you go to build in Xcode, because it's calling Gradle and says embed and sign task cannot be used in a project with dependencies to pods. So it's that pod pointing to ditto Objective-C that it does not like. It's in the documentation, but the documentation hasn't been changed yet. So I hope this moves somewhere else, because this is very, very handy because it generates all kinds of stuff. Okay, so looking at code. When you're writing Kotlin multi-platform code, you're going to have common made code that has these expect keywords. where I expect this thing, and it's basically like an interface. Each target that you support has to have an, actual. So you'll actually get errors in the iOS and Android side until you satisfy all those actual things. And you can create global functions, but that just seems messy to me. So I actually did an expect class, which is a beta API that you have to opt into. And it's weird that you don't have to put expect on each of the methods, because when you look at the implementation, you have to do actual on the class, you have to do actual on the constructor, you have to do actual on everything that matches up to that API. So maybe that's coming. Maybe they're going to add expect to that. But this is the Android implementation of that. I have to implement all those things that said expected because the compiler is expecting them. And inside of these methods, this is platform specific. So this is code that will only run on Android, and then iOS might be different. This actually looks basically the same, but I'll take a quick detour into the actual code where, like, on Android main, I'm calling into our Ditto APIs, but over on iOS, we have things like ditto. So iOS Objective-C has no namespacing, so namespacing conventions are in the class name. And yeah, these are the actual Objective-C classes, or rather a Kotlin view into them. What's really cool that it did behind the scenes, just by adding that CocoaPods entry, is it created all of these KNM files. Now the KNM files are binary, but you can look in them in Android Studio just by command clicking down on them, and you can see the API that it generated. It created, Kotlin X, C interop, but it's like, here's all of my Objective-C classes suddenly in Kotlin, and I can use Kotlin to interact with it. So it's very powerful. Now, some of the things that came through are not that great, and so if you want to get into customizing them, which is the next thing I'm going to be looking into, you really have to get into invoking the C interop command yourself. So that gets messy very quickly, which is why I started with just the CocoaPods thing. But you can customize it, and you can control that so that types are bridged better. Okay. So how does this actually work? Well, I'm evaluating Kotlin multi-platform from one perspective. I'm looking at potentially replacing some of the layers within our SDK, because the Ditto SDK is actually cross-platform Rust. So we interact with a C FFI style interface into the Rust from every language that we support. And there's a bunch of code generation and messy C++ here and there, and it's really ugly. And it's always the worst to be dealing with function pointers and that sort of thing. And so it'd be really nice to have Kotlin at the API level and Kotlin at the bridging level. And I see Kotlin multi-platform as a way to do that. But also we might actually add support for Kotlin multi-platform, because I was surprised how easy this was. And the demo app I'm going to show in just a sec is open source, so you could download it, play around with it. You do have to get a token from the Ditto portal. I'll add instructions for that in the README, but it's pretty easy. All right, enough talk. Let's see this thing. Okay, so what we have here is 2 pixels on the right and an iPhone on the left. Ditto sync is currently off, so I'm going to turn it on. And what you're going to see up at the top is our presence view. This is a web view with some JavaScript graphing, which is going to visualize the mesh network. So the blue lines are Bluetooth, and the pink line is peer-to-peer Wi-Fi. So the Mi to Pixel, this is the Pixel 6 to the Pixel 8, has Wi-Fi aware, and the iPhone, it's just Bluetooth connection to that. So there's our mesh, and now, ooh, somebody's not updating. It's always the Pixel 8. All right. So I took that offline to see if it would update. Oh, data went the other way. One of these devices, actually the Pixel 8, I forgot to put it on airplane mode, but that does have a service, but the other 2 have no internet connection. It's only peer-to-peer. Oh yeah, and I'm going to change color Wow, the Pixel 8 is not working. Let me relaunch the app. All right, start sync. Let's see if it picks up the data. Demo fail. All right, so my Pixel 8 is not getting the data. But let's add another device and see what else breaks. It's weird. The data can go from it, but not back to it. It's got to be my setup of the app here. But actually, the Pixel 6 and the iPhone are talking well. But you can see, now that we have 4 devices, notice the iPad and the iPhone actually have a pink line. So they have AWDL, peer-to-peer Wi-Fi between them, and the Pixels have peer-to-peer Wi-Fi, but it's Bluetooth across the Apple Android boundary. But like this is all like automatic. That's Ditto doing it, and I just told Ditto to do stuff. Awesome. So I can take a device offline. You can see the mesh like adjusts. I can actually let me make everything red and come back online, and we'll see what happens. Come on, Pixel. All right. The iPad that you can't see actually updated, but yeah, this guy's not reading for some reason. I suspect the data's flowing, but my UI is broken. All right, so that's it working. You can see it's pretty rough because this was slapped together, but the magic is really all in Ditto. I'm just like bridging it into a new paradigm and seeing what the pain points are. Oh wait, we're over here. Which country are we going to? All right, so that's all I've got. I'm Ben, I work on the Android SDK, and I'm hoping to work on Kotlin multi-platform support. So I guess we have some time for questions if anybody has them. Yeah, up front.
Yeah, which IDE did you use? And can you compile iOS artifacts on a non-Mac machine?
What was the first part of your question?
Which IDE did you use?
Oh, which IDE? I used Android Studio. I have played around with just IntelliJ IDEA, but the multi-platform plugin that you can put in both works great. However, I did not use the Android view. The Android view is really confusing for multi-platform. Because you get all these like Apple test, Apple main, native test. Those folders don't even exist. Like, why is that there? Why are you showing me that stuff? I think maybe if I wanted a piece of code across all my native targets, you could add stuff to the folder that's not there, create the native main folder. That's probably what it's for. But it's confusing when I only support, 2 platforms and the cross-platform. So I'm always looking at it from the, the project view. Because that's telling me, okay, here's my iOS app, and here's this stuff. Compiling. Compilation of, well, you can compile Objective-C, like on Linux. Objective-C is actually open source. Swift is too, but like, I guess you can compile Swift on Linux nowadays, but the problem is the iOS-specific frameworks come with Xcode. So inside Xcode is like the iOS and the macOS SDK, and you can actually download them independently now. So like if you wanted to do Vision OS, you can download that too. So those are all bundled inside Xcode, and Xcode is Mac only. Porting that to another platform, like some of those are proprietary frameworks. So I've heard of efforts to do that, but that's not something, that's bridging all of Apple's work to another platform. That's way more work than I'm looking into. But yeah, if you were compiling some basic, like Swift, you could do that on Linux. But if you're targeting iOS or Mac OS, you're going to need Xcode. That's the bottom line. Yeah, question?
What happened to Bonjour and Zero?
So when I was talking about LAN, I forgot to mention MDNS, or multicast DNS, is effectively Bonjour. So Bonjour is Apple's protocol for finding printers or other devices so that you can do stuff. That is what requires the broadcast ability. It is a broadcast. So that still exists. I think Apple still uses that under the covers. A few years ago, there was a bug about your devices like getting numbers after them because it kept finding them and then renaming them. Actually, the Android SDK that we have used to use an MDNS library for Android and Java that literally just wraps Apple's Bonjour implementation. We don't use that now. We now use a Rust MDNS implementation, but it still exists.
I went to the Swift talk yesterday in Chatelain, so it seems like everybody's saying, time to pick up Rust, right?
So, yeah.
This is Python. It's like you need both.
Well, it depends. Like Python's very widely used in AI, but like on your question about Rust, like why do we use Rust? Rust is very safe. That's the number one reason. It is very opinionated. Compile times are slow because it does a lot of static analysis and creates very safe, very fast native code. It also supports conditional compilation so that you can say, you know, this stuff is only applicable to WASM, this stuff only applies to, you know, iOS. But you would use it at systems level most of the time for, you know, doing low-level stuff. So it's comparable to C++, but newer and safer. Some people complain about the ergonomics of Rust, but that's really how opinionated Rust is. You have to learn how to program with Rust because Rust forces you to program safely. So, yeah. Question?
I have a question on the comment.
Yeah.
My question is it possible to apply layer of security to the peer-to-peer communication, whatever encryption?
Mm-hmm.
And my comment is you can compile iOS with non-iOS device, but based on iOS terms of services, that is illegal, and you might become liable if you go to production.
Sorry, what was your first question?
Can you apply layer of security?
Oh, the layer of
peer-to-peer network?
Okay, so specifically on the security for peer-to-peer, we actually do encryption on the wire. So it's basically like TLS or something on the wire. But we do ditto. Two peers need certificates that match in order to connect. So if you have like two Ditto apps, they're going to have different app IDs, and their certificates are going to have that app ID baked into them, and they won't match. We also have a way where you could actually encode permissions in the certificate, which would control like maybe you in a certain role don't have access to write certain documents, but you can read them, and someone else can write those documents. So that actually gets encoded in the certificate. We do support encryption on disk for iOS. That's a paid feature, but I don't believe we've rolled that out to other platforms, but it's certainly doable. I don't know too many details about the actual security, but one more thing about the connections. We have an API where programmatically you can actually deny requests. So after the handshake, application level logic could say, no, I don't want to connect to this for whatever reason. Question in the front?
How do you deal with the timestamps to synchronize them across devices?
Yeah, so the question was, how do you deal with timestamps to synchronize across devices? So it boils down to something called a hybrid logical clock. And I'm not an expert on this, but it's basically the device's timestamp plus some kind of number, like an integer. And the integer is always counting up, and then the timestamp is what I think the time is. So those might not match up. You know, you might be in a different time zone or your clock is skewed. But over time, looking at those, you can see a pattern like, I know these things are after each other, and this one came so many milliseconds after the other one because this is message number 2 from you. And that was, you know, you can look at the delta between those and also look at how long it took and do some bookkeeping to go, I think your clock is 4 seconds ahead of mine. So that's a short summary, but it's hybrid logical clock. And we're at time. Thank you all for coming.